to if there are questions on the chat, I might not be able to. When I'm when I'm sharing my screen, it's not so easy to have access to the chat, so I might not notice that there are questions in the chat. So please, I mean, interrupt me, in particular you, Alfie, if you notice that there are questions in the chat. Please do interrupt me and so that the question can be asked. Okay, so this is more or less the outline of what I plan to do. So I'm going to start today with some introduction and talk about the representations of the simple Lie algebra sl₂. I mean, the reason for this is twofold. One, what I will discuss about the representations of sl₂ is kind of very typical of a certain kind of representation theory. And so, you know, it's not just for the sake of knowing what the representations of sl₂ are, but mostly for the sake of getting introduced to certain techniques and certain ways of working, which will be useful when we discuss generalized Weyl algebras. And the other reason is that one of the main examples of a generalized Weyl algebra, or one of the important examples of a generalized Weyl algebra, is precisely related to sl₂. It's the enveloping algebra of sl₂. Okay, so these are the two reasons why I want to start with this. Then I will move on to talking about generalized Weyl algebras, defining them, discussing some properties, giving a lot of examples and constructions, and then finally move on to weight modules for generalized Weyl algebras. And if time allows, I mean, this is for the whole lecture series, not for today. If time allows, I will discuss other types of representations for generalized Weyl algebras. Okay, but this really depends on the time that we have. So let me start, and I want to. So first of all, I'm sorry. I know Alfie used K for a field. I'm more used to F. So I mean, I could have tried to stick with the K, but then at some point I would change into an F without noticing. So I think it's better to do from the beginning. I'll use the F. So F will denote a field. Most of the time, you can consider it to be an algebraically closed field of characteristic 0. If you want, think of it as the complex numbers. And I want to connect with something that Alfie mentioned, which was the representations of a polynomial ring in one variable. And as Alfie explained, these are exactly, I mean, they're parametrized precisely by the pairs VF, where V is a vector space, finite or infinite dimensional, doesn't matter, and F is an endomorphism of this vector space. This describes completely the representations of the polynomial ring in one variable. Okay. Now, a question we can ask is, well, when are two of these representations isomorphic? So I'm denoting the representation associated to the endomorphism F and vector space V as VF, okay? So when are VF and VG isomorphic? Okay, well, I'm already using the same base space because, I mean, if two representations are isomorphic, they have to have the same dimension. The underlying vector space needs to have the same dimension. So I mean, I'm assuming the underlying vector space is the same. This is no loss of generality. So in this context, when would these two be isomorphic? I'm not sure if Alfie discussed isomorphism of representations. No, just letting you know. And this is what I kind of remembered, but I wasn't sure. But I mean, it's very easy. I mean, you will guess it because, I mean, an isomorphism of any algebraic structure is just a one-to-one onto correspondence between the two structures that respects the structure, whatever the structure is. So an isomorphism between two vector spaces is a bijective function which respects the underlying operations, which would be addition and scalar multiplication. So in other words, a linear map which is invertible. Okay, an isomorphism of groups is just a bijection between two groups which respects the group operation. Okay, an isomorphism of rings, it's a bijection between the two rings which respects all of the operations, and that means, and here we need to be a little bit careful, which means addition, multiplication, and I'm considering the unit to be an operation, a zero array operation. So it must send a unit to the unit element to the unit element. Okay, so for representations, it's the same thing. So an isomorphism will just be a bijective map. So let me write it like this: A from VF to VG. So representations of this algebra are vector spaces. So A must be an invertible linear map. In other words, is in GLV. But this must also respect the module structure. And this means that A, if I have some element of the polynomial ring, let's say P of X, acting on V, this action takes place in VF. So if I wanted to be extra careful, but I don't, I would write an F here to remind you that this is the action in VF, is the same as P of X times A of V. And here the action would be in the module VG. So I could, but I won't anymore, put in a G there to denote this. So this is the condition. This is just saying that up to a change of coordinates, essentially the action is the same. If I change coordinates and the actions look the same. So this would be the condition. Okay. Well, it's easy to see that it's enough to verify this for the variable x. And for the variable x, what I have here inside, remember I'm acting via f, so this is just a of f of v. And on the other side, I have x is acting, but on the module vg, so that x is acting via g. This is g of a of v. Okay. And for example, if I replace, if I call w A of V, this needs to be true for every v in V. So if I replace v with w, this is just saying that g of w is equal to a of f of a inverse w. In other words, this is saying that g is equal to af a inverse. Okay, this is a little bit more clearly here. This is the condition. Okay, so the two endomorphisms must be conjugate under the general linear group. Okay, and this says that the isomorphism classes correspond precisely to the endomorphisms of a vector space up to conjugation. And there's a characterization of that called the rational canonical form. For example, if the field is algebraically closed, we could use the Jordan canonical form. This is a unique form that characterizes endomorphisms up to conjugation. Okay, so when we learned linear algebra and when we learned about these canonical forms, we were really learning about the isomorphism classes of representations of this polynomial ring in one variable. Okay, so the point of this is, well, not only to pick up on an example, a very good example that Alfie had given in her lecture, but also to make the point that in general, representation theory is kind of a massive generalization of linear algebra. Okay, in linear algebra, we're studying linear maps, endomorphisms, canonical forms, eigenspaces, eigenvalues, eigenvectors, diagonalization, and all of this. And representation theory generalizes this to a general setting where you don't have only when you don't have only one transformation, but maybe you have two or three transformations. And for example, you want to see if you can simultaneously diagonalize all three transformations, if there's a basis relative to which all three are diagonalizable or upper triangularizable or something or other. Okay, so this is what representation theory is about. For example, in this context, if we're looking at representations of the polynomial ring in two variables, we would be really looking at a vector space and two endomorphisms of this vector space. And if we wanted to classify this by isomorphism, we would really be looking sorry, I forgot to say, if I'm dealing with representations of the polynomial ring of the commutative polynomial ring in two variables, these two endomorphisms must commute, okay, with each other. And if I'm looking at isomorphism classes, I would be looking at pairs of these commuting transformations under conjugation. So some kind of rational canonical form, but a simultaneous rational canonical form for two endomorphisms. Okay, so a basis which would simultaneously give me a certain kind of matrix for both of these transformations. Okay, if I'm looking for representations of the free algebra on two generators, if you're not familiar with that, it's just, just remove the commutativity condition and just say, okay, any two endomorphisms of a vector space. And if I'm looking at the isomorphism classes there, I would be looking at, you give me any two arbitrary endomorphisms of the same vector space, and how can I characterize them simultaneously? What can I say about them simultaneously? Okay. Fortunately, in this generality for the free algebra in two variables, you cannot say very much. But in most algebras, we won't be dealing with free algebras, and there is a great deal that we can say. Okay, so this is essentially what representation theory is about in a certain sense. So, for example, going back to the example of the polynomial ring, if you assume if you assume that the field is algebraically closed and the vector space is finite dimensional, well, what I'm going to say next doesn't require that, but afterwards it will. I'm not sure if Alfie talked about submodules. No, okay, but you can also guess what a submodule is. It's just a substructure, right? So it would be a subspace of the original space, which is also stable under the action. Okay, for which the action on the original module induces an action on the subspace. So in the case that we're dealing with, an invariant subspace is just a subvector space, a subspace of the original vector space, which is invariant under the endomorphism F. Invariant, with this understanding. Here it's not an equality, it's a containment. Invariant in this sense. Okay, so a submodule would be something like this. Okay, a subspace which is stable or invariant under the action of the endomorphism F. And if I'm looking at simple or irreducible submodules, I know this was also not defined, but a simple submodule is a submodule which is as small as possible in the sense that it has no other submodules except zero and itself. It's the usual definition for algebraic structures. Okay, so it's a non-zero submodule which has no other submodules besides itself and the zero subspace. Okay, so in this situation, what would be the simple submodules? So the smallest possible irreducible, the smallest possible invariant subspaces. Well, since my field is algebraically closed and my vector space is finite dimensional, I know that there will be eigenvalues, and so there will be eigenvectors. So there will be a one-dimensional subspace. I just take any eigenvector, and the one-dimensional space that it spans will be a subspace which will be invariant because the endomorphism will just send that vector to a multiple of itself. So it will preserve that subspace. So in this context, the simple submodules correspond essentially to eigenvectors. So the study of eigenvectors is in a certain sense corresponds under the conditions that I posed corresponds to the study of the simple representations of the polynomial ring in one variable. Okay? And as I said, if the field is algebraically closed, they're just one-dimensional and they correspond to the eigenvectors of the transformation. Okay, so for example, this is again is usual. When we have a simple object, we wish to try to describe an arbitrary object in terms of the simple objects. So for example, if I have a positive integer, I will try to decompose it as a product of prime numbers. And we know that this is possible. Prime numbers here would be the simple objects, okay? Well, describing one of these modules as a direct sum of simple modules essentially corresponds to diagonalizing the endomorphism. Okay, so whether or not an endomorphism is diagonalizable really boils down to the question, can this specific representation be written as a direct sum of simple subrepresentations? Okay, so the problem of diagonalization in this case corresponds to decomposition into a direct sum of simples. Okay, which is nice, and it's interesting because we know that this is not always possible. Right? So some endomorphisms are diagonalizable and some are not. And this is what happens in representation theory. Certain representations are direct sums of simple ones and some others are not. Okay? That's the way life is, okay? But there's a few things that we can do about this. Well, one is if you look at the Jordan canonical form, you'll have these Jordan blocks. And each one of these Jordan blocks will determine an invariant subspace, which although in general it will not be simple, so it will not be one-dimensional, it's in a certain sense indecomposable in the sense that I cannot break it up into a direct sum of other things. Okay, so we already, again, in representation theory, we're confronted, I mean, in linear algebra, we're confronted with this idea that, okay, if my endomorphism is not diagonalizable, I can still break down my vector space into a direct sum of certain subspaces, which correspond to kind of the smallest blocks, even though they're not simple, they're indecomposable. I cannot decompose them anymore into smaller direct sums. Okay, so this is it. But I mean, I won't be talking much about indecomposable modules. I'll be talking more about simple modules. So even when your representation is not a direct sum of simples, looking at simples may give you some ideas specifically. So in the situation that I mentioned, the endomorphism, since my field is algebraically closed and the dimension is finite, there's always a basis. Even, I mean, we don't need to go as far as Jordan canonical form. We can just, aim for less, and it's easy to see that there will be a basis relative which my endomorphism will be upper triangular like this. Okay, and when I have it upper triangular like this, I can find a lot of subrepresentations, a lot of invariant subspaces. Here's one, the vector that corresponds to this column here will give me a one-dimensional subspace. And the vector space spanned by the vectors corresponding to these two columns, because of this form, this tells me that this vector space is invariant under the transformation F, okay? And I can continue this way, okay? Which means that my vector space V, although it's not a direct sum of simples, I can kind of filter it, okay? Considering, it depends on where you want to start. I mean, I started from one-dimensional and I started going up, but you can always also go down. I start with the whole space, and then I found, say, the space size dimension n, and then I found an invariant subspace of dimension n-1, and then one of dimension n-2 contained in it, and so forth. So I get this filtration, and I just go down in dimension one by one. This sometimes is called the complete flag. It's something very, very important that comes up in algebraic geometry, in topology, and so forth. Okay, and what's meaningful is that when I look at these quotients, these will naturally be modules. They will be one-dimensional modules, so they will be simple. And what are these quotients recording? Well, they don't tell me everything about my representation V, but they're really just recording these diagonal entries. So even if my transformation F, my endomorphism F, is not diagonalizable, just looking at the simples, looking at these chains here, this is called the composition series, for those of you who know that, just looking at these composition series will give me a lot of information, will give me the eigenvalues. And people who work in applied mathematics, I don't know if there's any anyone of that kind here in this this chat. I'm certainly not of that kind, but people know that I mean, eigenvalues already tell you a lot about your endomorphism. Okay, so this is interesting. So this is kind of an overview. This is kind of my introduction. I don't know if there are any questions. Yeah, I'll assume that's a no. So I will start with sl₂. So I'm not assuming that people know what Lie algebras are or anything like this. If you know, that's great. But if you don't, it's also great. Okay. So I'm just going to give you an example, which is sl₂. So this is just 2 by 2 matrices of trace 0. So it's a set of matrices that have trace 0. So it's a vector space that has dimension 3, because essentially, I mean, 2 by 2 matrices has dimension 4, and the condition that the trace is 0 reduces the dimension by 1. Okay, so clearly a very natural basis is just given by these elements. Here, this strictly upper triangular, this strictly lower triangular, and this diagonal matrix that has trace 0. This forms a basis of this Lie algebra. And why do I call it a Lie algebra? Because it has an operation. Okay, the operation is not matrix multiplication, because if you multiply 2 matrices of trace 0, then in general you will not get a matrix of trace 0. For example, if you multiply this matrix here with itself, you get the identity matrix, which has trace 2, which is not 0 unless your field has characteristic 2. Okay, so this is not an algebra in the sense that Alfie talked about, but it's a different kind of algebra. So it's not I can define another operation on this algebra called a Lie bracket, which has different properties, which do not include associativity. And this operation is really just the commutator of 2 matrices. Okay, so the Lie product of H with E is HE minus EH. And this is guaranteed to have trace 0, because we know that the trace of a product in one direction is equal to the trace of the product in the other direction. Okay, so when I make this difference, I'm guaranteed to have a matrix of trace 0. So this is guaranteed to be in sl₂. So it's an operation which is closed. So the result is in sl₂, and well, it satisfies, for those of you who know it, I mean, it's a bilinear operation as multiplication is, but it's anti-symmetric, and instead of the associativity condition, it satisfies something called the Jacobi identity. Okay, which I won't discuss. So this is the operation. So let's try this operation on these two pairs, H with E. So H, remember, this is probably the easiest way to do the calculation. H in terms of matrix units is E11 minus E22. Here it is. And E is the matrix unit E21. So this way it's easy to do the computation, and you find out that it's 2 times E. If you do the same thing, this commutator between H and F, you get minus 2F. And if you do the commutator of E and F, you get H. Okay, and so these are the magical conditions. So this is extremely important. This is one of the most important examples in representation theory, for reasons that you'll maybe catch a glimpse of in this lecture. I won't develop much on this, but I mean, it's really, I mean, the names that I've given to these matrices are completely classical, and I mean, they should be used. So E will always be this particular matrix, F will always be this matrix, and H will always be this matrix. And these very nice relations, so H with E is 2 times E, H with F is minus 2 times F, is kind of saying that multiplication by H, and here when I say multiplication, I mean this commutator. So multiplication by H is a diagonalizable transformation, because it sends E to 2 times E. So E will be an eigenvector with eigenvalue 2. It sends F to minus 2F. So F will be an eigenvector with eigenvalue minus 2. And of course, it sends H to 0, because the commutator of H with H is H squared minus H squared, which is 0. So H is another eigenvector with eigenvalue 0. And that's it. that covers all three basis vectors of SL2. So the action of H is very nice. It's diagonalizable with very nice eigenvalues, 2, 0, -2, so completely symmetric. Okay, and this is very nice and very important. So I want to discuss representations of the sl₂ algebra. Okay, I mean, for those of you who are wondering, the sl₂ algebra there are many interpretations of the sl₂ algebra. The classical one is that it's related to a group, which is the group of 2 by 2 matrices of determinant 1. Okay, and so, if you do the exponential of a matrix of trace 0, you will always get a matrix of determinant 1. Okay, so this gives a connection between this vector space, which has a very nice structure, is just a three-dimensional vector space, and the very complicated group, which is the group SL2 with capital letters, which is the group of 2 by 2 matrices of determinant 1, which is really a very nice group with connections with essentially everything. And studying representations of the sl₂ algebra essentially recovers the representations of the Lie group. Okay, so that's what we're going to do. So what is a representation of the sl₂ algebra? Without going into formalities, it's really just, like we did for polynomial ring in one variable, and we discussed briefly polynomial ring in two variables, or the free algebra on two variables. It's just determining three endomorphisms of a certain vector space V, one corresponding to the action of E, one corresponding to the action of H, and one corresponding to the action of F. Okay, and these three endomorphisms, like in the representations of the commutative polynomial ring, they would have to commute. Here, they would have to somehow satisfy the relations of your Lie algebra. And those relations are that the commutator of H and E is going to be equal to 2 times E. And the commutator of H and F is going to be equal to -2F. And the commutator of E and F should be H. So a representation of SL2 is just given by three endomorphisms of a certain vector space, of any vector space, that satisfy these two relations. Okay, and this might look a little bit odd and in fact difficult. It's not, off the top of my head, can I think of three endomorphisms that have this property? And if I start playing around with matrices, this is, for example, let's do an experiment. I hadn't planned on this. For example, the easiest kind of matrix is the 1 by 1 matrix, right? It's just a scalar, right? So imagine that E, H, and F are just scalars, numbers. So I'd be looking for one-dimensional representations of SL2. What are the solutions to this equation, thinking of E, F, and H as just a scalar? Well, HE minus EH is just 0, right? So this is saying that 2 times the scalar E is equal to 0. And if I'm not in characteristic 2, this means that E is equal to 0. So the element E in the Lie algebra would have to act as 0 on a one-dimensional module. Same goes for F, okay? F will have to act as 0, okay? And the same goes for H, because again, EF minus FE, if E and F are just scalars and not matrices, this would be 0. So there's only one representation of SL2 that has dimension 1, and it seems like a very non-interesting representation. It has dimension 1, and all of the elements of SL2 act as 0. Okay, well, this is called a trivial representation for reasons for which you might guess. So we've just found out all of the representations of dimension 1. If we wanted to find all of the representations of dimension 2, then we would have to turn H, E, and F into 2 by 2 matrices and solve these equations. And this would not be a pleasant task, nor an easy task. And that's where the methods of representation theory come in to help you. And very soon you'll be knowing a lot of representations of SL2. In a certain sense, you'll be knowing all of the representations, all of the finite dimensional representations of SL2, okay? Using certain methods from representation theory, which I will introduce very, very, very soon, okay? So if you want to, and this is kind of a good idea, to reduce this to associative things, now it's not difficult. Once we have these three endomorphisms, or if you prefer these three matrices, I mean, if I act with the element E twice, that's essentially acting with the square of the matrix E. And matrix multiplication is associative. So, I mean, once you have this representation, you can really think that, okay, I have these three matrices, they will generate a certain associative subalgebra of the algebra of all endomorphisms of V, okay, which will have E squared, it will have H times E. Recall that H times E, if you're not familiar with Lie algebras, this might be confusing. H times E is not an element of your Lie algebra. Your Lie algebra only knows, for example, H squared, as I mentioned. H squared is not an element of your Lie algebra. But I can act by H, and I can act again by H. And this will correspond to applying this endomorphism H twice. So that's acting by H squared. Okay, so essentially we can reduce to the associative case if you want, and you just look at the associative subalgebra of the endomorphisms of V generated by these three particular endomorphisms of these three matrices, if you prefer to think of matrices. Okay, I mean, for those of you who know more, what I'm really trying to do is somehow introducing the enveloping algebra of the Lie algebra without getting into technicalities. Okay, but we don't need to. Okay, very good. So how can we study representations of the Lie algebra? Well, there is an obvious one because this Lie algebra is 2 by 2 matrices. And 2 by 2 matrices are designed to act on 2 by 1 column vectors. That's what they're made to do, right? Okay, so a natural representation is looking at these 2 by 1 column vectors. Okay, and have the Lie algebra element E act as this matrix here, as this transformation, this element F act as this transformation, and this element H act as this transformation. I mean, this is essentially what the Lie algebra is asking me to do, right? It's like when you have an element, a permutation, the permutation is asking you, please, can I permute these n numbers, right? And here it's the same thing. SL2 is asking me to act in this way, okay? Although it can act in many, many other ways. But let's start looking at this. So let's fix a basis for this, for these column vectors. So I'm calling the first element of the canonical basis, so say the column, if you want the column vector 1, 0, calling it X, and the basis element 0, 1, I'm calling it Y. It's not very usual to give these names to basis elements, but you'll see why I want to do this, okay? And so how's the action of E, how's the action of F, how's the action of H, okay? This is not very difficult, and I want to represent it with a diagram, okay? So here's my basis vector X, here's my basis vector Y, and I'm going to represent the action of E in green color. So let's see. Oh, sorry, that's not what I wanted to do. This is what I want to do. So what does E do? Well, let's look at E here. E acts by this transformation. So it means that it kills the first vector and it sends the second one to the first one. Okay, so this is telling me that it kills X. So E, I'm going to represent it like this, sends X to 0. I shouldn't have to put in an E here because I'm using the color green, but just to remind you, and it sends the second vector to the first vector, so it sends X to Y. I'm not using the label E because it's redundant. So this is what E is doing. Okay, what is F doing? So again, if we look at this matrix, F is sending the first basis vector to the second one, and it's killing the second one. Okay, so let's represent this. So F sends X to Y, and it's killing the second one. So here, it's doing this. And finally, what is H doing? Well, H is acting diagonally, so I'll represent this as loops. So H will send X to 1 times X, that's the eigenvalue, and it will send Y to -1 times Y. Okay? So I have my first, well, technically it's my second representation of SL2. I have the one-dimensional representation, which we discussed, and this is a two-dimensional representation of SL2, which can be depicted in a very, very nice way. Okay, so I think I have the same drawing here. Okay, here I put in dotted lines because usually we don't draw these last arrows because we assume that, I mean, E is going in this direction, so if there's nothing more in this direction, it will mean that it kills it. That's the understanding. And F is going in this direction, so if there's nothing to the left of Y, I would assume that F is killing Y, and this is just a convention to make the picture a little nicer, okay? And so here we have a two-dimensional representation of SL2, and it has a very nice diagram form, okay? So what else can we do? Okay, the first lesson of representation theory that I taught you was, I mean, follow what the algebra is telling you. In this case, the algebra was 2 by 2 matrices, so it's telling me I want to act on column vectors. We did this, and we have a representation. Okay, let's soon find other lessons, but I think what I have planned for now is not yet that. So I want to discuss simplicity. Is this a simple representation or is this not a simple representation? I forgot to say before, while I'm saying this, you can look at, I mean, I have added definitions for sub-representation and simple representation. So following something that Alfie mentioned and proved, which is modules are the same thing as representations. So following this idea, I mean, if you're dealing with modules, you'll often say simple module. If you're dealing with representations, you'll often say irreducible representation. Okay? But modules and representations are the same thing. I mean, I really cannot even distinguish them. So I will use indistinguishably, I mean, the word simple and irreducible, so I'll even combine these. I will say an irreducible module and a simple representation if I have to. It doesn't matter. It's all the same. Okay? So, question, is this a simple representation of SL2? Well, it's two-dimensional, so it's non-zero. So the question is there a subspace which is invariant under this action? Is there a proper subspace which is invariant under this action? So let's find out. So imagine, so this representation is called V. So let's suppose that there is some sub-representation, W. So I'm not writing it, but I'm assuming that W is not just a subspace. I'm assuming that it's a sub-representation, so it absorbs the action of SL2. And let's assume that it's non-zero. So if it's non-zero, it has some non-zero vector there, which is called, let's call it, for example, so linear combination of x and y, let's call it lambda x plus mu y, okay? And I mean, if it's non-zero, one of these two scalars is not zero. So let's assume, for example, that lambda is not zero. The case is very similar. So what can I do here? So this is an element, I'm assuming this is an element in W. So when I act by SL2 on this element, I will still land in W. I will still be inside W because I'm assuming that W is a sub-representation. Okay, so what can I do? I can, for example, act by F. And when I act by F, F times W, on the one hand, I know this must be an element in W. Okay, but what is the action of F on W? Well, F acts on X. What does F do to X? It sends X to Y. Okay, so this will be lambda Y. And what does F do to Y? It kills it. So that's it. Okay, so lambda times Y is in W. Okay, and since lambda is not zero, I conclude that Y is in W. But if Y is in W, then when I act with E, I must also land in W. But when I act by E, E times Y, E acting on Y is equal to X. So X is also in W. So if W contains a basis, W must be equal to everything. And so we've just proved that if we have a sub-representation which is non-zero, it must be equal to V. So this shows that V only has two sub-representations, which is 0 and itself. So this shows that our representation is simple. Okay, so I gave this with a lot of detail. I won't be giving this much detail anymore, but I mean, in most cases, you can just do variations of this reasoning and you'll arrive at the same conclusions. Okay, so not only did we find a two-dimensional representation of SL2, but we found a simple one. Just to remind you all, the one-dimensional representation has to be simple because there's no way of getting any representation in between the zero-dimensional and the one-dimensional. Okay, so we already have two simple representations of SL2. Well, it's better than nothing. This representation has a name, a typical name, which is L1. Okay, and you might be curious why 1, because it's two-dimensional. It's true, but the 1 is encoding the largest eigenvalue of H. So we've seen that H acts diagonally on this representation. Okay, there's an eigenvector with eigenvalue 1 and an eigenvector with eigenvalue -1, and I'm recording the largest eigenvalue of H. Okay, this might not seem relevant, but I mean, we will find that this will tell me everything that I need to know about the representation. Okay, so this is why I'm recording it. Okay, so we have this representation. So what next? Well, one technique that you can use in representation theory of certain things, and what I mean by certain things are, for example, Lie algebras and groups, is consider an action. So what we have, I have an action of SL2 on this two-dimensional vector space generated by X and Y. When I'm studying representations of groups, or when I'm studying representations of Lie algebras, or more generally, when I'm studying representations of Hopf algebras, I will always have, well, forget about Hopf algebras for now, because this is not necessarily true what I'm going to say next. If I have a representation of a group or of a Lie algebra, I will always have a representation on the symmetric algebra of this vector space. What do I mean by the symmetric algebra of this vector space if you haven't heard about this before? It's essentially thinking of X and Y as variables, and this reveals why I called these basis elements X and Y, and think of them as polynomials. So the symmetric algebra, for example, on a vector space of dimension 2, is just a polynomial algebra on two variables. And what are these variables? Well, you choose any basis of your vector space, and the variables will correspond to the spaces. Okay? And so we will formally consider things like x squared times y, and so forth. I'm assuming that the variables commute. Okay, so I have an action of SL2 now on this polynomial ring in two variables. But I have to tell you, how is this action done? I mean, I cannot just decide to do whatever I want, because in principle, it will not give me an action. It will not give me a module. It will not respect the relations of SL2. So one thing that will work for Lie algebras is an action as if you were doing a derivative. Imagine that you're using the Leibniz rule. You're taking the derivative of a product. What is the derivative of a product? You act on each factor of the product, and you add up all of the possibilities. Okay, so what do I mean here? How would E act on the monomial x to the k times y to the L? Well, E will act on the first factor and leave all of the other factors alone, plus E will act on the second factor and leave the first factor and the remaining factors alone, and so forth. E will act on the last x that appears, and we'll leave everything else alone, and then E will start acting on the y's and so forth, as if you were taking a derivative. Okay? So what happens when you do this? So I have a reminder here to remind me that E kills x and E sends y to x. So all of these first terms will be 0 because E acting on x will be 0. So all of the terms up to here are going to be 0. Then when I get here, E acting on y, that means x. So I'm going to replace this E acting on y with an x. And I'm going to do this in every slot. They're L slots, and they will all look the same because this is a commutative polynomial ring. So I will get L times something. And what is that something? Well, I replace one of the y's with an x, which means that I'm going to boost the power of x to k plus 1, and I'm going to reduce 1 to the power of y. So this is the end result. And this will remind you of something. This will look like you did a partial derivative, right? So this action on the polynomials is exactly the same thing as doing a partial derivative with respect to y, and then multiplying by x. So E is acting on this polynomial ring as this differential operator, which is very interesting, okay? We start with nothing, and we have an action with differential operators on the polynomial ring. No wonder why Lie algebras are important in the study of differential equations, okay? So I can do the same thing with f. I can play the same game, and if you play the same game with f, now f will kill y, and it will send x to y. Okay, so if you play the same game, you find that this is how f acts on this monomial, and this is the same thing as doing a partial derivative with respect to x, and then multiplying by y. So f is acting as this differential operator, and h is acting semi-simply again on these polynomials. It's just recording, I mean, you do the same calculation, I'm going to repeat it, and the end result, it's recording the exponent of x minus the exponent of y. So sometimes this is called kind of an Eulerian kind of derivation. So this is the corresponding differential operator. So now I have a very interesting action of the Lie algebra sl₂ on the polynomial ring in two variables. Notice that the polynomial ring in two variables, it's an infinite dimensional vector space. So we started with a two-dimensional representation, and we ended up with a representation on an infinite dimensional vector space. Okay? Well, if you don't like infinite dimensional vector spaces, you're probably in the wrong course, because that's what I like. But in any case, in this particular case, you shouldn't be sad because I mean, let's look at these formulas with a pair of eyes. Okay, what is E doing? It's kind of bringing one y over to the x. What is F doing? It's bringing one x over to the y's. And what is H doing? Well, it's just multiplying by a factor. So we see that there's one thing that never changes here, which is the total degree of the monomial. If I start with a monomial of total degree 37, if I act by E, or if I act by F, or if I act by H, the end result will also be a monomial of degree 37. Okay, so this will tell me that if I consider just a homogeneous, all possible homogeneous polynomials of a fixed degree, that will be a subrepresentation. It will be stable under the action of E, F, and H because E, F, and H are not changing the total degree. So what this tells me is that this polynomial algebra here, I can break it up into the homogeneous components, where by homogeneous components, I'm referring to the total degree. So this will be the homogeneous component of polynomials of total degree m. Okay, what's a natural basis for the space of polynomials of total degree m? Well, here's one: x to the m minus 1 times y, x to the m minus 1, y to the m. Okay, this is a natural basis. So this space has dimension m plus 1, and it's a representation for sl₂. So if you're not interested in infinite dimensional representations of sl₂, we've just found a lot of finite dimensional representations of sl₂. Okay, in fact, one for every dimension, right? If you want a representation of dimension 37, you look at S36 V, and this will be a representation of sl₂ of dimension 37. So now all of a sudden, we found infinitely many finite dimensional representations of sl₂, one for each dimension. So now we have a lot. Okay. So the first natural question, well, there are many natural questions, but one natural question is, okay, well, there are two natural questions for me. One is, what do these representations look like? And are they simple? Okay, well, it's better to answer them in the order that I gave by chance, because I mean, to try to test if it's simple or not, I need to understand what the action is. So let's first try to understand what the action is. Okay, so this is what I want to do. I mean, I know what the action is. It's by these differential operators, but let's be specific. And it turns out that I should probably renormalize my base. I mean, the action is already very nice, but to make it look like, you know, what in the end the theory will tell us, I will want to renormalize the base. So instead of taking just these plain monomials, sorry, instead of just taking these plain monomials here, I want to scale them slightly, okay? And I want to scale them with these binomial coefficients. After all, we like combinatorics, and so it doesn't hurt to add a binomial coefficient to one of these monomials. Maybe this will look nice. I mean, we know that when you're taking partial derivatives, the binomial coefficients make these derivatives look nicer, okay? So if I renormalize the basis, and now I compute the action of E, F, and H. So how does E act on this basis element Vk, which is this monomial here? Well, remember that E was acting as what? Partial derivative with respect to y, and then multiply by x. Okay, so we take the partial derivative with respect to y, so here's the k, and we multiply by x, so we add 1 to this exponent. And then, of course, this will resemble the basis vector vk minus 1, but so we need to play a little bit with this binomial coefficient. I'll leave that up to you. You can write it like this, and so you can write it like this. So E sends vk into a multiple of vk minus 1. You can do the same, I mean, so E is kind of going down on the indices, and when it hits 0, E will kill it. Okay, and F will be going up. You know, it's the same kind of calculation. I won't do it again. So E will send Vk into k plus 1 times Vk plus 1. And H, how does H act on Vk? Well, H was really just recording the exponents, so it's going to be m minus k minus k. So m minus 2k. H will be acting just by multiplication by m minus 2k on the basis vector vk. So guided by the first example of the representation of dimension 2, I can write this out like this. Okay, I can put in these basis vectors v0, v1, v2, up to vm. Okay, this forms a basis of the space of homogeneous polynomials, and I'm going to record the action of E, F, and H using these colors like I did before. Okay, and you see that this is really, I mean, this is just follows from what I've written here, so I won't go into detail. It's these formulas, but you see when you look at it like this, you see that okay, H is acting by eigenvalues. The largest eigenvalue is m. And then you start subtracting 2 and subtract 2 and subtract 2 until you reach the eigenvalue minus m. So very symmetric. Then E is going up, is going up, but in the way that I've drawn it, it's going to the right, and it's decreasing the indices until it reaches V0, and then it kills V0. F is going in the opposite direction, raising the indices until it reaches Vm, and then it kills Vm. And I mean, when E goes up, it multiplies by a certain scalar. When F goes down, it multiplies by a certain scalar. And I mean, I made that change of basis. I renormalized the basis so that these scalars would be very nice. It essentially just start writing the numbers from 1 up to m, and then write them in the reverse order from 1 up to m, and there you have it. Or another way to think about it is that, you know, the sum of these parallel edges is always going to be equal to m plus 1. That's another way to think about it. So this is the representation of this module, which was homogeneous polynomials of degree m. Okay. Following what I did for the two-dimensional representation, I'm going to call this representation L of m, recording the highest eigenvalue of h. Okay. So we have a very nice schematic representation of the representation. Okay. So the question is this an irreducible representation? Is this simple? Okay. And I'm going to leave that up to you. I know the time is running up. I'm going to leave that up to you. I'm going to give you a couple of hints. Well, I'm going to give you the punchline. Yes, it is an irreducible representation. But to make sure that you understand what you're doing and are not just relying on what I'm saying, I'm going to make this harder. Okay. First, I'm going to give you a general element, a general reasoning. So if we call this representation as before, we could do it. I'm not going to use green. Maybe we call this representation. We know that it's called L of m, but in this particular case, let's just call it V. We can do the same thing. Take a sub-representation, assume it's not zero. So it will be a linear combination of these vectors. Okay. Some of the coefficients will be zero, some will not, but some coefficient will be non-zero. So you can, I mean, if you represent the linear combination like this in this order, you can look at kind of the last one, which is non-zero. So imagine this one. So this coefficient is zero and this coefficient is zero. So imagine this is the leading coefficient, okay? Which means that the coefficient of V2 is not zero. Well, if I start acting by red, which is f, if I start acting by f, these will start be going down until I reach a non-zero multiple, because none of these numbers are zero, a non-zero multiple of Vm. So kind of hand waving, this will guarantee that the submodule W must contain a non-zero multiple of Vm. So it must contain Vm. And if it contains Vm, now you act by E, it must contain Vm minus 1. And you act by E, it must contain Vk, and so forth. I mean, that was a big jump. It must contain Vm minus 2, and so forth, until you reach V0. So you see that it must contain everything. So as before, W must be equal to V. So this is a sketch of what you can do. I said I was going to make this a little bit harder just to make sure that you know what you're doing, which is the following. I have been assuming that the characteristic is zero. But in fact, this representation is simple even if the characteristic is not zero. So my question is, what's the condition on the characteristic for this module to be simple? Okay. So if you want to make sure that you understand what we did, you will be able to answer this question. Because, I mean, the only thing is, well, again, I'll give you a hint. Where did I use the characteristic in this? I said, okay, there's a linear combination here. Let's look at the leading coefficient, which is non-zero. It was here. That's all fine. I'm not using characteristic. And I said, well, now let's act with f to get a multiple of Vm. What multiple is it? I start with a non-zero multiple of V2. If I want, I can even, I mean, the coefficient is non-zero, so I could even divide by that coefficient and assume that the coefficient here is 1, not a problem, okay? When I start applying f, I will be multiplying by these numbers. And I said, well, these numbers are not zero. So then I can divide by them. And this is where the characteristic will play a role. Okay, so this is the hint that you need. Just to make sure that you understand, I won't be discussing much characteristics other than zero, but it's just to make sure that you understand what you're doing. If you can exactly pinpoint what's the, if the characteristic is in this range, it will be simple. If it's not in this range, it will not be simple, and I can find an example of a submodule which is neither zero nor equal to V. So I think I will stop here, but I will remind you of two things. One, we started from nothing and we've constructed infinitely many simple representations of SL2, one for every dimension. Number one observation that I want to make. Two, these representations are interesting not only because they're simple, also because their action is related to differential operators. Number three, the SLE algebra, you might not have thought much about it. It's just a three-dimensional Lie algebra, very small, right? Three-dimensional vector space, but it has infinitely many irreducible representations. I haven't discussed this, but it even has irreducible representations which are infinite dimensional. No finite group has this property, right? If you start with any finite group, it will have finitely many irreducible representations. Okay, so even though we thought that this was kind of something laughable, a three-dimensional thing, and this three-dimensional object encodes a lot of things. Okay, encodes all of these infinite dimensional irreducible representations. They're all non-isomorphic for an obvious reasoning, which is they all have different dimensions, so they cannot be isomorphic to each other. Okay, so I thought I had something else to say, but I don't remember, so I'll stop here.